This talk I'm giving is based on a tutorial, actually on two tutorials, one that we gave at CIR last year and the web conference this year. I made those tutorials together with Rolf Jagerman and Professor Maarten de Rijke. So credit to them for helping with some of these slides. What I've done is I've taken the tutorial and made it a lot smaller so that we can talk about it in, I'll talk for 40 minutes or less, hopefully. And I don't want to go into too much technical depth and have it serve more as an introduction. And because you are a company, I also added some advice that I've given to a lot of, based on my experience with giving talks at previous companies and the things I've seen there. So let's get started. I'm going to focus on counterfactual learning to rank from user interactions. And I'll start with just an introduction on the ranking and learning to rank topics, in case you're not as familiar. You probably know that learning to rank is it's vital for information retrieval. Anywhere where you have search or recommendation, you usually have a ranking system. With a ranking system, I mean any system that outputs a list of items. These items can be web pages or products or videos or whatever. And the important part is that you want the right items in the right order. So if the output is multiple items sorted or ranked, you have a ranking system. Of course, you know web search. So on this example, we have Google, but a recommendation example might be Netflix or some other video platform recommending you series and movies. Behind both of these systems is some ranking model that takes all of the available items and decides what to display, right? So clearly a core task. I think everyone has seen these systems before, and probably some of you are working on these systems right now. What the traditional way of optimizing such a system, so improving a ranking system, was supervised. So if we go back 30 years when this sort of these ideas really started to take form in machine learning, they used annotated data sets, which are still often being used, where you have relevance annotations for a query and a document pair provided by human experts or judges. So that means that you have a bunch of experts that you've trained, because it requires quite some training usually for these people to understand what is relevant and not. You show them, for instance, a web page and a query, and then you ask them, how relevant is this web page for this query? And if you do that long enough, you can create a data set, and if you have a data set, it's quite easy to train your model. However, over the past couple of years, the last, let's say, 10 years or so, the limitations of this approach have become very apparent. Some of the most important limitations here are, first, this approach is very expensive. It's quite expensive and time-consuming to make these data sets. This is not something you can crowdsource. You really need experts, and experts are expensive, or you have to train them, which is also very expensive. They can be unethical in certain cases. So to create a data set, for instance, if you're ranking personal emails or personal files or anything that's privacy sensitive, you don't want experts to look at someone else's emails or documents from a different company, etc. So in these cases, you can't really make a data set because you're not allowed to look at the data, have experts look at the data in detail. It can also be impossible. Think about personalization. If you're ranking for if you're ranking for web search, it's what is relevant, people generally agree. But if you're ranking things to sell, for instance, very often people vary in what they find nice and what they don't in their personal preferences. There are no experts that can help you there, right? If you were to create a data set, if you were to recommend me a movie, you probably have no idea what I like. So you wouldn't be able to create a data set for me either. So in these cases, this is not going to work either. They're stationary, even though we know that what's relevant changes over time. So we've observed in sort of user behavior that people change their opinion on what's relevant, but a data set remains the same, of course, unless you update it. So there's also a sort of a time limit on how applicable your data set is. And most importantly, it turns out that in many cases, the actual user preferences and the preference of the experts or the annotators aren't perfectly aligned. So the experts don't agree with the users. And now this is a really big problem, because it means even if you learn perfectly, if you have a perfect machine learning algorithm that 100% perfectly captures the preferences in the data set, you still don't have the optimal ranking system, because the data set and the actual users don't agree about which documents are better than others. So there's clearly a need for an alternative to learn from. I don't want to say that you shouldn't use annotated data sets. They're very important. They have an important role to play still. But it's clear that we would like some other way of learning that doesn't have these limitations. And what we'll talk about today is an obvious answer to this problem, which is learning from user interactions. You can probably guess that a lot of the problems that we saw on the previous slide are solved with user interactions. For instance, if you have users, most companies that have a service or a website have a lot of users, and interactions then are virtually free. If people are using your system, you'll observe interactions. And of course, user behavior is indicative of their preferences. People usually behave in ways for which you can derive their preferences from. So this seems to solve the problems that we saw with these annotated data sets made by experts, but it also brings their own problems, because user interactions are a form of implicit feedback. Practically never do you get interactions that tell you, I prefer this over this, or I prefer this by this much. You have to turn that implicit feedback into a signal that you can learn from. The difficulties there are twofold. On the one hand, we have noise, and on the other hand, we have bias. So in this talk, I'll focus on clicks, because that's usually the most important signal. But a lot of these findings go for a lot of other forms of feedback as well, or interactions as well. So first we have noise. People click for many unexpected reasons. People might be looking for something, you show them something radically different, unrelated, and they might still be interested. Users tend to trust their search engines as well, or their recommendation systems. So if something is on rank number 1, even if it has nothing to do with what they're looking for, they may still click on it because they trust the system to give them a good item. So you'll see a lot of clicks for unexpected reasons. And very often you'll see clicks happen despite there being no preference. So something isn't relevant, people might still click. The opposite also occurs very often. People may not click even though it's something that they would like, something that's relevant. That might be because they don't realize it. It might be because they didn't even look at the item. It might be because they got distracted. There's many unexpected reasons. This isn't a problem per se if it's noise, because noise, the effect of noise disappears if you have a lot of data. So if you have millions of clicks, the effects of noise disappear. What doesn't disappear, and what is the biggest problem, is bias. So bias comes from the fact that there are other factors that also affect user interactions, or clicks in this case, that are not relevancy. So there are other things that cause some items to be more clicked than others. The most important one, the one I'm going to focus on today, is position bias. When you show a ranking of items, when you show a number of items in an order, people don't pay the same amount of attention to all the items. So people will mostly focus on the top items and focus much less the bottom items. Sometimes they won't even look there. And this will have an effect on the number of clicks that you'll see. There are also other forms. You have item selection bias, for instance. If you're often when you're doing recommendation, you do top K recommendation. So you're only showing K items. For instance, you might only be showing 5 products to a user. Now, of course, the user is not going to click on anything that's not in that top 5 because they can't, right? You didn't show them anything else. So you're going to see more clicks on the items that you displayed than you didn't display because the user doesn't have a choice there. That's also going to affect the number of clicks that you see on some items and on other items. And this list goes on for a long time. I'll mention one more important one, which is presentation bias. So often the results are presented differently, and as a result will also be treated differently. On a lot of video websites, there might be a really large trailer displaying on top, and you might have small thumbnails everywhere else. Now, of course, people are going to look at the trailer much more than those small thumbnails. So the way that you present it, if you have a radically different presentation for some items than for other items, is also going to affect the way people interact with something. In practically all the talks I give, I show this one figure because I think it shows the problem very clearly. This is an eye tracking study. They had a large number of people search for a digital camera, I believe, and followed based on their eye movements where they were looking on the screen. So that's what we see over here. This is what we call the golden triangle. And this red color over here indicates that 100% of all users looked at the top 2 results. So everyone that was looking for this camera, everyone that typed in the query, looked at the top 2 results. But then if we look at the result number 8 down here, we see this bluish shade of color. And this indicates that less than 50% of people looked at the item down there. So if we're learning from clicks, and if we're inferring preferences from clicks, this is going to have a really large effect, right? If we see the same number of clicks, the same click-through rate up here than down here, that probably means that the item down here is much more preferred to the item up here, right? If we see, let's say I see 20% of people click here and 20% of people click down there, probably this item is much better because half of the people didn't even look that far down the list and still it received the same number of clicks. So the position bias here really acts as a filter which makes you see less clicks further down the list than on top. The goal of unbiased learning to rank is to optimize a ranking system or a ranker with respect to the relevance preferences of the user. So what does the user prefer? Which items does the user want to see or want to click on? And then we want to learn that from user interactions. Now, the only way that we can do that correctly is if we avoid being affected by other factors such as position bias. And we call these factors biases because we don't want to be influenced by them. So to find the optimal ranking system from user interactions, we have to make sure that we avoid the effect of these biases. And that's the goal of unbiased learning to rank. I don't claim that we have methods that can remove every type of bias, but it's the goal. I think the name unbiased learning to rank overstates its purpose because nothing is ever going to be 100% unbiased, but it's kind of the moonshot, you might say. All right. Do you have any questions for me before I continue? All right. Then what I'm going to do is I'm going to start with discussing counterfactual evaluation, and then we're going to go into counterfactual learning to rank. The evaluation part is actually much more important. If you can do evaluation, you can do the learning as well. And right. So what we've seen so far is that we don't want to work with annotated data sets, but we may still want to, it's still really important to evaluate a ranking system. If you have a new ranking model behind your service, you want to know whether it's good or not before you deploy it. And we don't want to do this with annotated data sets. We also don't want to do it with without deploying it, like with an A/B test. So the question in counterfactual evaluation is, can we evaluate a ranking system, a ranking model, you might also say, without deploying it or annotated data? So simply based on user interactions. So what we'll do is we'll have a new ranking function, which I'll call f-theta, and we're going to evaluate it using historical interaction data, in this case clicks, that were collected from a previously deployed ranking function, f-deploy. So I have my clicks based on f-deploy, the current system, the system that's running right now, and I have a new system that I've never deployed, and I want to know how good it is without deploying it or using any type of annotations. And that's the goal of counterfactual evaluation. Right, before I get started, before we get into the counterfactual part, let's consider the easy case where you have your true relevance labels. Let's say that I know exactly what's relevant and what isn't. I'm going to keep it simple for this talk. So I'm going to denote relevance with the Y. So this is the relevance for document DI. It's either going to be 0 or 1. We have binary relevance. And you can do this for any information retrieval metric, recall, precision, etc. For this talk, I'm going to minimize average relevant position. And we'll do that just by taking the sum over all documents. So I'm going to sum over all the items that I'm ranking. Then look at the rank that an item gets according to the new model, and then multiply that with the relevance. So this basically gives me the sum of ranks of the relevant documents. You can average that by the number of relevant documents if you divide by that number. The goal here is the rank should be as low as possible, because the lower the rank, the higher these items are in the ranking. The less a user has to scroll, the more likely the user is to see the item. Right, so this is an extremely basic scenario. Of course, if I know what's relevant and what isn't relevant, this is very easy. Right, so here we have a visualization, 5 documents. Document 1 and 4 is relevant, everything else isn't. It's very easy to calculate the average relevant position here if I know where the relevant documents are. The problem, of course, is that you never know the true relevance labels. Of course, you can use annotated data, but we've seen the problems there. So we want to learn it from clicks. We want to evaluate average relevant position, but based on clicks. The problem here is clicks are both biased and noisy, but they are an indicator that a document is relevant. And particularly if a click is missing, it doesn't mean that something isn't relevant. If we go back to this visualization, if you show this ranking to a user, the user might observe the first document, like it, it's relevant to what it's looking for, so it gives it a click. Continue to the next document, it doesn't like it, so it doesn't click there. Third document, for some reason it thinks maybe this is what I'm looking for, even though it's not really relevant. And then stop looking. So the user, for whatever reason, might say, okay, I'm done here, I don't want to keep scrolling. So even though the fourth document is relevant, we don't see a click there. Same for the fifth document. So we see that, similar to the picture in the golden triangle, both the relevance and the position of a document going to affect the amount of clicks that we see. And what we want to do is, from all these reasons, to basically separate the relevance from, for instance, the observance. And what's important to remember here is that a lot of randomness happens in these clicks, but as long as it's noise, you can average the effect away if you have a lot of data. If it's bias, it's not going to help you. If you can have millions of clicks and you'll still have that bias. The picture I showed you before was based on a large number of items, of users, and we still see position bias. It's not going to go away if you get more samples, basically. All right, so what I'm going to do is I'm going to mathematically describe the problem and the solution. So if we understand exactly how bias affects our metrics or metrics estimation, we can correct for it. And this is the main idea of counterfactual evaluation. I'm going to simplify the situation, of course, because we have to make some assumptions. And we do that by separating examination and relevance. So first we have the problem. So in order to model a click, so a click is modeled by examination and relevance. The first part, a document being examined, sometimes we say observed, we mean the same thing. So I'm going to note OI is 1 if item number I or document number I was observed. So there's a probability that someone's going to look at a document. It's based on the ranking that you display it in. So based on where you show a document, people might look at it or they might not look at it. The second part is whether someone will click on it or not, and we're going to assume that that's only conditioned on whether someone observed it and whether it's relevant or not. So first someone looks at an item and then they decide to click on it or not based on how relevant it is in this model. And clicks only occur on examined items. So if no one is going to click on something that they didn't look at first. So the probability of a click, we can model it like for every click we know it's also observed. And we're basically taking the probability of, well, let's start over here. The probability of the item, the document being observed, times the document being clicked given that it's observed. So we're decomposing the probability that someone's going to look at something and the probability that someone's going to click on something, given that they already looked at it. That's the probability of a click. This is, of course, a very simple model. Real user behavior is much more complicated. The point here is, even if we have this really simple model, we'll see that you'll have bias. And if you correct for bias, assuming this very simple model, you'll already see quite some performance gains in your actual systems. All right. So I hope this is clear. And we have a probability of examination and a probability of a click. And given that it's examined, and the probability of a click is basically the probability that an item is clicked and examined, which is just the probability of examination times the conditional probability of a click conditioned on that it's examined. I can't see your faces, so I hope everyone is with me here. Otherwise,
yes,
yeah, great. Yes. Usually I see if students are nodding. All right, thanks. So I'm just going to start with the naive way. We can ignore this entire idea of bias and just say if something is clicked, that means it's relevant. If it's not clicked, that means it is not relevant. So I have the same metric as before, the average relevance rank, but now I've replaced this relevance function with a click. And what we can do then is for now, I'll assume there's no noise. So people click if something is observed and relevant. They don't click if something is observed and not relevant. So it's an extreme simplification. And still we have bias here. So the way that we can prove that is by taking the expectation over this examination variable. So we can rewrite this as the sum of all the documents that were examined and relevant. Those are the clicked items under our assumed model. If we take the expectation over this metric, we basically get the summation over all the relevant items, the probability that an item was observed in the ranking that you displayed, times the rank under the new model. So this is sometimes a bit confusing. The probability of examination is based on your current ranking system, so the system you use to collect clicks. The rank function over here is based on the new model, the model that you're evaluating. And of course, this is a problem, right? Because the performance of the new model has nothing to do with the previous model. But we can see here that in expectation, it's going to affect our evaluation metric. And this is, of course, exactly what we don't want. We don't want the evaluation of the new model to be affected by the way that we collected these clicks. We can specifically see what's going to happen with our metric in that we can see here that it's weighing or weighting these documents according to the examination probability during logging. So a document will have a higher weight in expectation because it's more likely to be examined. And we know from position bias, from eye tracking studies, etc., that if you show a document at a higher rank, it's more likely to be examined. So what happens is a sort of a logging policy confirming behavior. The items that you showed at a high rank during logging are more likely to be clicked because you showed them at a high rank. So they're also more likely to be considered more relevant. So you can have an unfair advantage when you're evaluating a model that puts the same documents at a very high rank because it's matching the position bias that you see during logging. Right, so items that were displayed at high ranks when you were collecting clicks are going to have an unfair advantage if you don't correct for position bias. That's what we see here. Maybe this is a little bit complicated because we're doing it live in a presentation now, but if you go back to the slides later, you'll see that this is what I'm doing here is not advanced mathematics, right? I'm just calculating an expectation, and it's already showing us that we have a problem here. Of course, I'm here to talk about the solution. The main solution right now in counterfactual learning rank is the methods are based around inverse propensity scoring. And the idea behind inverse propensity scoring is very simple. It's if we know the examination probabilities, then we know the advantage that a document gets from logging, and we can basically divide that advantage away. So this is the IPS scoring function, the estimator. So based on some clicks, a new ranking function, and the documents that were ranking, what happens is that we still sum over all the documents. The click is still treated as a relevant signal, but each click is divided by the probability of examination during logging. And we still have the rank of the new system, right? So what happens here is that for a single interaction, so for, say, one time, if you show a query or a ranking once, you have your vector of clicks. You take the rank of every document that was clicked, but then you divide it by the probability of examination. So what happens is that documents that have a higher probability of examination will have a smaller weight, whereas if there was very little chance of being examined, there's going to be very high weight. And if you take the average of this over many queries, so I'm just showing it for a single query here, but if you show it for many times where you showed this ranking, we can prove that this is unbiased. The intuition behind it is, if you think back to that picture of the golden triangle, if we know that only half of people look at an item at a certain rank, then when we show a rank there, we show an item there at that rank, and it's clicked, we can weigh the click times 2. So we can take the click times 2, and that times 2 is to correct for the fact that half of the people haven't even looked there. So it's as if you get the click-through rate as if you were showing it somewhere where everyone looked at it. And that's why it's called counterfactual. And this is an unbiased estimate. We can prove it quite easily. I'm doing the same trick I did before. I'm taking the expectation over this estimator, where we take the expectation over this probability of observance, this observance variable. The same thing happens. We can rewrite this sum as the sum over all the documents that were observed and relevant. But this time, we were dividing by the probability of examination. So probability of examination again appears in the denominator, just as in the previous example, but now it's divided away by the IPS estimator. So you end up with the sum over all the ranks of all the relevant documents. And this is exactly what we're trying to estimate in the first place. Of course, this is an expectation. You would have to take a large number of clicks for this to work. But in the previous example, that wasn't true. With this naive estimator, if you had 1 million clicks, you would still have this bias. Here, on the long term, it disappears. I hope this is clear.
Yes.
We can. Yes. Otherwise,
yes. I have a question.
Sure. Yes. Yeah.
So that probability of observation, it's given a specific ranking, right? So.
Yep.
But usually in a real world scenario, we're going to have multiple different rankings throughout time, right? Does that affect this?
Yeah. You have to know. So there's two ways of dealing with it. The earliest way is the easiest way, I guess, is if you when you log the click. So when someone clicks and you log it in your data, you should also log the rank at which the click took place. And because then you can calculate this probability of observance, of examination, sorry. So you need to keep track of where was this item being shown. Yes.
Okay, so that R just means the position where it was.
Yeah, R is the ranking in this case.
Okay.
And from the
ranking of that document.
The list of items that you showed, and you can derive the ranking from it.
Okay.
Yes. I'll say a little bit more about this in the next part because it's really important. So I'll go to the next part. This is evaluation. The real question is, how do you do learning? Of course, I don't want to go into too much detail here because it's very complicated, or it's more complicated in a boring way, right? In that it gets very technical and it's not very interesting. There are some papers that you can read on this topic if you want to do the implementation. So I'm, for instance, this paper by Agarwal. To restate what we've seen so far, the idea of the IPS estimator is that you reweigh your clicks. So some clicks are reweighted inversely to the probability of examination. So the more likely someone is to look at something, the lower the weight. If people very rarely look at something, the higher the weight to compensate that less people are looking at it. During learning, you want to find your ranking system, in this case that maximizes, or I should say minimizes, the ARP, so the average relevance position, should be as low as possible. The idea is that with unbiased evaluation, you can estimate that using this estimator. And now we want to change the ranking function, so this part up here, so that this has the lowest value. That's the main idea. And you can do this by adjusting standard learning to rank methods. Again, for time, I'm not going to go into details here. I did want to show you sort of what that looks like. So these are results from a simulation. They're based on real queries and real documents, but there's no real users clicking. The clicks are simulated. And they're simulated with a lot of noise and bias as well. This is just to show that even in a simulation with noise and bias, some methods work and some methods don't. Let me explain what's happening here. So on the y-axis, we have the average relevant position. The lower, the better. Here we have the number of training clicks. Note that this is a log scale all the way from 1,000 to 100 million. This red line is the production system. This is the system we use to gather clicks. So this is where the clicks come from. This is what I call an oracle. In a simulation, we know exactly what preferences are. So we can train a model to perfectly match those preferences. So this is the optimal model. And this here is the naive estimator. This is the first estimator I showed you that ignores the effective bias. And what we see is very typical bias behavior. So it does learn, it does improve itself. It even improves over the production system, but it's stuck, right? So if you have, say, 20,000 clicks or 100 million clicks, there's no difference, even though it hasn't found the optimal model yet. And this is typical bias behavior. So getting more data doesn't improve the system anymore. It's a clear indication of bias. The IPS estimator, if you use that to learn, the other estimator I've shown you, it has a higher variance, and as a result, initially performs more poorly. But as you get more clicks, you do end up with the optimal system. There are tricks you can do to move this line from at the beginning down there. I'm not going to go into that, but the main point here is that with the IPS estimator, getting more data always improves the system, whereas with the naive estimator, you don't know. You don't know where you end up in. In this case, it's an improvement. It doesn't have to be. It could also have been converged over here where there was no improvement. So that's the difference between biased behavior and unbiased behavior in this case. There's also papers that apply this to real-world scenarios. So think of query completion in Gmail and Google Drive. Archive, we also know that Search in Archive has done experiments with IPS optimization. They all found significant improvements using IPS. So we also know it works outside of these simulations, of course. But you can't have nice graphs there. You only see differences in click-through rate. All right. There's one important part that I haven't talked about yet that you probably realize that we should talk about, which is I've assumed that we know these probabilities of examination. Of course, that's not trivial. We need some way to estimate them. The key assumption that most works make right now is that the probability of examination only depends on the rank at of the document. So this sort of goes back to your question you asked me earlier. In this case, we only need to know at what rank was the document displayed when we saw the click, and what was the probability that at that rank you would be examined. So we want to estimate per rank how likely someone to click there. This is the most simple algorithm, which is random top n, where you just take your top n, in this case we have top 4, and you shuffle it. So you show, for instance, this ranking, you show another random ranking, etc. You show a lot of these shuffled rankings. And what happens is that at every rank, all of these documents are equally likely to have been displayed. So relevance has no effect on the click-through rate here because the average relevancy per rank is the same because it's completely shuffled. So differences in click-through rate are only going to be caused by the rank, the position bias. So this is a really effective way of estimating position bias very quickly. I've seen companies do it. However, there's a clear downside, right? If you have a good system, you don't want to shuffle all your results because it's going to result in horrible performance for your user, a really negative user experience. So there's two solutions to that. One is to minimize the randomization. The first method is rand pair, where at each time you only swap 2 documents. So instead of the entire ranking, you shuffle the order of only 2. More recent work has looked at what they call interventional sets. So very often you have inherent randomness. For instance, if you do A/B testing. If you do A/B testing, you have at the same time a ranking from system A and a ranking from system B in order to move some of these items. And that randomness can also help you to estimate position bias. And you don't have to do any additional experiments if you have A/B tests running. There's also some methods that do it without randomization, usually based on expectation maximization. These are less effective, so there's no randomization required, but these often don't work as well because you have to estimate relevancy based on features. So It's nice you don't need randomization, but they're less reliable. All right. I'm going to end the presentation with some advice that I've seen. This was not part of the tutorial, but I've given talks like this at over a dozen companies at this point. And usually in the discussions I have afterwards, I find we talk about a lot of the same advice. So I wanted to present that to you. I don't know if this is applicable to you per se. We haven't discussed these things yet, but it might be. It might also be very obvious. So don't. This is not tailored for you. This is just what I generally see helps if you want to apply counterfactual learning to rank. There are 5 steps that I think you need. Let's go through them in order. The first thing I always ask a company tell them before they should start doing anything in counterfactual evaluation or counterfactual learning to rank is whether they have A/B testing running. Because in the end, you want some reliable way to compare 2 systems, and A/B testing is just the most reliable way that we have still. So I wouldn't start looking at the counterfactual evaluation before you have A/B testing. Again, I don't know the situation that you have. We'll talk about it afterwards. My next piece of advice is to log everything that you can about user interactions. So the actions that a user takes, the query, did they click, did they purchase, how long did they look at a page, the actions by the system. So we've seen that it's important to know at what rank you display an item, but it's also important to know what text that you display, what was the layout, what was the price of an item, everything basically that is being the actions taken by the system and the information displayed. Same goes for item features, etc. And contextual information. If you know the time and date, whatever you know about the user exactly, all of this is really useful if you want to learn offline in a counterfactual way. Of course, I want to disclaim I'm not a lawyer, so I know there's laws about what you can and cannot log. And there's also ethical sides, so please check that with your own department, of course. The next part is position bias estimation. So before you can do any learning or evaluation, you need to understand the user bias. I've shown you that by shuffling items you can do it, but you can also randomly swap pairs of items through A/B testing, or even without any randomization. And this will give you a model of this position bias that you can use in the next steps. It's good to remember that bias depends on your ranking layout. So if you change the way your website looks or your results are displayed and it looks completely different, it probably is going to affect the bias, right? People are going to look at your website differently, so you might have to re-estimate position bias. Otherwise, usually it's quite static. So it's not something that changes every week, or maybe not even every year. If you have the model of position bias, then you can perform counterfactual learning to rank. So, and what happens here is that a lot of choices have to be made. You have to think about what features are your ranking model going to use. You want to develop new features. What kind of model, right? There you have linear models, neural models, all kinds of architectures and the parameters of the model and the optimization process. What's really nice about counterfactual learning to rank is that you can make all these choices without deployment using unbiased evaluation. So you can both estimate the performance of a system and optimize it without deployment with the techniques I've shown you before. And I've heard from places where they've taken this approach that they've seen a massive speed boost in research and development because you can now already tell how good a model is before you've done any A/B testing. You can iterate much faster, for instance. So there are some real benefits to this approach. Of course, I want to say don't blindly trust anything. There's a lot of things that can go wrong here, right? You could have your wrong bias model, have the wrong assumptions, bugs in your code, etc. So that's why I started with A/B testing. It's always good to have A/B testing to make sure that on the long term you're not losing touch of your real user preferences. All right, and with that, I'll conclude with my takeaway messages. We talked today about supervised approaches to learning to rank and their limitations. Specifically that annotations from experts usually disagree with your actual users. User interactions can solve this problem, but they bring noise and bias. Noise is not such a big deal, but bias really is, because it doesn't go away if you have a lot of data. Counterfactual approaches allow for unbiased learning to rank. You can remove specific biases like position bias during learning and evaluation. It only requires randomization when you're inferring a user model, and you can even do without that. Once you understand the bias, you can remove its effect from any evaluation. And of course, the main takeaway, if you use this, you can predict improvements without deployment, which is a really, really big advantage. All right. Before I end it, I want to say, just to be clear, when we say unbiased learning to rank, I mean unbiased with respect to position bias. There's a lot more biases that you should be aware of. So don't think that this trick gets rid of all of that in one go. Yeah, thank you very much.
Thank you.
Thanks. So thanks for the talk. I think that was a really simple and end-to-end overview of the problem. So thank you for that, Harry. Right?
Yes, yeah. I'll show my references very quickly.
Yes, yes.